Hey, so today in this video, I'm gonna do notes set 15, gases. So unit 3, as you've noticed, kind of goes on and on and on and on and on. And so this is the section, we already talked about solids. This is the section on gases. So let me flip my camera, we'll get started. So something that's unique about gases is that gases are, for our purposes, gases are the only state of matter that's able to exert pressure. So this is kind of like when we were talking about vapor pressure. Anything to do with pressure is dealing with the transition either from the liquid to the gas or just the gas itself having pressure. Pressure equals force divided by area. The force is the particles pushing, and the area is the space that it's applied to. So the force distributed over an area is pressure. Gases uniformly fill any container. They're easily compressed because gases have lots of space between the molecules, whereas the other two states, liquids and solids, they're touching. So the space between the molecules is actually what's being minimized when a gas is compressed. And like I said before, gases exert pressure. So pressure is a really, really important thing with gases. So down here, we're going to have lots of ways of measuring pressure. The barometer, it's a machine, it's a device, kind of like a thermometer measures temperature, but a barometer measures pressure. But that wasn't enough, apparently. We had to come up with like several other ways to measure it. So Evangelista Torticelli over here, this guy, he came up with the barometer, and notice his name, T-O-R-R, Torricelli. One of the units that we use to measure pressure is kind of named after him, a torr. 760 torr is equal to, all of these things represent the same amount, but the ones that I think are most important is an atmosphere. This one I think is the most important. 1 atmosphere is the amount of pressure that you feel, here's you on Earth, and we've got our atmosphere. And the atmosphere is pushing down. You don't really feel it so much. But the amount that the atmosphere is pushing on you when you are at sea level, that is 1 atmosphere. So if you go up to the top of a mountain, here's you on a mountain up here, you have less than 1 atmosphere of pressure because the distance that the atmosphere has to push on you is less. That one's important. Some other ones, a mmHg is, at least it's practical. What this stands for, mmHg, mm is millimeter, Hg stands for mercury, and in the old thermometers, they used to use mercury. So when sorry, did I say thermometers? They did use thermometers, but in the sense of pressure, it was a similar idea where you would have your container, and depending on how much the pressure would go up or down, you could measure the millimeters that the mercury was moving. So that's why we have millimeters of mercury. A torr is the same thing as a millimeter of mercury, just named after this guy. Pascal is another one. It is a Newton per meter squared. It is a force over an area. I don't really use that one. The most common one that we're going to be using a lot, as you can see down here, kind of looking at the preview, is going to be either atmospheres, and occasionally you might need a torr, but atmosphere is the number one. These three scientists here, these rather handsome dudes, maybe not, I don't know. There's something about him that I don't like. I think it's like his head and like chin ratio is a little off. I don't know. But look at how cute he is. He's like got little dimples. Anyway, these three gentlemen were scientists around in, as you can see, kind of like the 1600s, 1700s to even 1800s. And they performed experiments and figured out the following laws. We've got Robert Boyle, who came up with Boyle's law. Jacques Charles with Charles' law. And Amadeo Avogadro with Avogadro's law. And I'll explain each of these kind of vaguely. So this is Boyle's law here. And what it's saying, it's PV1, so P1V1 equals P2V2. The product of pressure times volume is constant, provided a constant temperature. I'm going to move through these really fast, not because they're unimportant, but individually, there's really not much point learning all three of them, because what ends up happening is they get combined into the ideal gas law down here. And this is the one that we use the most. So all I'm doing is showing you how the ideal gas law came to be. Part of it was from Boyle's law. He helped us understand the relationship between P for pressure and V for volume. Pressure is going to be measured in atmospheres. Volume is going to be measured in liters. Charles' law helped us understand the relationship that gases have when you have the volume of a gas. And we're looking at the relationship with its temperature, but the temperature is measured in kelvins. To convert into kelvins, you take the Celsius, I don't know how to spell this, Celsius, and add 273. That's how you convert from Celsius to Kelvin temperatures. Avogadro's law gave us the relationship between the volume of the gas, how much space it's taking up, and how it relates to the number of particles, AKA, I'm going to change this, number of moles are in a sample. So pressure, volume, volume temperature, volume number of moles. Volume is like repeated in all of them, but we can combine these all together into the ideal gas law. And And the ideal gas law, like it says, was derived from the previously existing laws above. We've got PV equals nRT. It always to me looks like perv nerd, but I have a license plate sitting in my window outside of the classroom facing the hallway that has PV nRT on it. So now if you're wondering why I have that up, that's why I have it up. And the idea is, okay, PV, we know that that's pressure, volume. Reminder, pressure is in atmospheres, volume is in liters. Pressure times volume equals N is the number of moles. T is the temperature in Kelvin. And the only thing left is R. R is a necessary conversion in order to make all of these units work together. R is called the universal gas constant. And like I said, it's just a necessary number that we're going to put in for all of the equations to combine. R is given to you on the AP formula sheet. I'll give you 10 seconds here to grab your formula sheet so you can mark it and I can show you. 10, 9, 8, get your sheet. 7, 6, 5, did you get it? 4, 3, back table, did you get it? Okay, so 3, 2, 1. Here's the AP formula sheet, and you kind of have to use the units that are on there to figure out which R you need to use. Since our ideal gas law has atmospheres, liters, moles, and kelvins, we need to use the one that has atmospheres, liters, moles, kelvins. The negative exponents in the units are just formatting. I could rewrite this for you, and you can rewrite this for yourself if you prefer, as 0.08206 units, liters times atmospheres divided by moles times kelvins. Some people don't like to write this out as this fraction. So instead they'll do liters times atmospheres times moles to the -1, since it's in the denominator, times kelvins to the -1. That's what's going on up here. The important number is this 0.08206. So there's some homework problems that'll help solidify this idea of PV equals nRT. PV, put the little equal sign, equals nRT. Okay, so copy paste this equation into homework 15A. We're going to skip this first part for a second and go down to ideal gas law calculations using PV equals nRT, or variations of the gas laws. So the first one, number 3, says to find the volume of 0.300 grams SO2 gas. That's important because this is gas law calculations at 30 degrees Celsius and 400 torr. So PV equals nRT, but the problem is that P needs to be in atmospheres, and it's currently in torr. The temperature cannot be in Celsius. Can't be in Celsius. It needs to be converted to kelvins. And the number of moles, we don't have the number of moles, but we can get it if we do a grams to mole conversion. So let's do the easy one first. Converting temperature is pretty easy. Just like the notes said, to take your Celsius, add 273, and that's how you'll get from Celsius to Kelvin. So 30 degrees Celsius plus 273 equals we'll definitely want a calculator today. I left my calculator at school, so I have to use my husband's TI-89 titanium instead of my TI-84. But that's okay. So 30 plus 273 equals 303 Kelvin. Some other conversions we've got to do. If we have 400 torr, that needs to get to atmospheres. There are 760 torr in an atmosphere. 760 torrs is 1 atmosphere. So I've got like 400. I've got like about a half of an atmosphere, but we can see exactly how much of an atmosphere I have if I take my 400 divided by 760. And yep, about half. I have 0.5. I'll just keep a couple digits. 0.5 atmospheres. So now we have the pressure, temperature, and we need to get this into number of moles. 0.300 grams of SO2 The S weighs 32.06. Let's see. 32.06. I have S. What is it? SO2. SO2. So S plus O, oxygen, 16.00. I don't know how to use this calculator. Plus 16.00. So SO2 here is weighing 64.06 grams per mole. 64.06 grams for 1 mole of SO2. So when I figure this out, let's see, 0.3 divided by 64.06 equals, I have this many moles, 0.00468. So plugging into my equation, PV equals nRT. I've got all the units correct. Pressure, 0.526 atmospheres. Volume, that's what we're solving for, so I don't know what it is. N is the number of moles, 0.00468. R, I copy and paste from the notes, 0.08206. 0.08206. T is the temperature in Kelvin, which is 303. I'm solving to find the volume. So, let's see, I'm gonna take my, gosh, I do not like this calculator. 0.00468 times 0.08206 times 303. And let's see if I can figure this out. And I feel like you guys, when you guys are like, you go so fast, and I'm like, I know, but I don't go very fast on this calculator. Okay, same thing, 0.00468 times that times 303. I'm going to divide the 0.526 across, and let's see what we get. 0.221. So my volume is what we were solving for. The volume that this gas would take up under these conditions is 0.221 liters of space. Okay, next problem. How many moles of oxygen will occupy a volume of 2.50 liters? That one's already good. 1.2 atmospheres, perfect. We don't have to convert. 25 degrees Celsius, that one we do need to convert by adding 273 to that number. So 25 plus 273 equals 298 Kelvin. We are solving for moles. We have the other variables. PV equals nRT. The pressure is 1.20 atmospheres. The volume in liters was 2.50 equals, I don't know the number of moles, I'm trying to find that. R is always 0.08206 from the formula page. And the temperature that I converted was 298. Let's see. Okay, for this one, I'm getting, oops, sorry, here's how I did it. For this one, I'm getting that N, my number of moles, is equal to 0.123 moles. So 1/10 of a mole of gas. So that should get you most of the way through. Some of the problems are a little bit trickier because you have the volume in milliliters instead of liters. You'll have to convert. Torr instead of atmospheres, you'll have to convert. Temperature in Celsius instead of Kelvin, you'll have to convert. You have grams instead of moles, convert, et cetera, et cetera, et cetera. So that's how these work. But overall, I think that the perv NERT problems, PV equals nRT, are pretty simple. One last thing. It was found by this guy, Sir Avogadro, that under standard conditions, that a mole of gas takes up 22.4 liters of space. That's how much 1 mole of a gas takes up. At STP, STP is, oh, it's already written up here. Standard temperature and pressure. Standard temperature and pressure is just what scientists came up with. Standard temperature, we say, is 0 degrees Celsius. Standard pressure is 1 atmosphere, which is 760 torr. The problems that we just got done doing in the homework, these were not under standard conditions. We had temperatures all over the place. This one was 30 degrees Celsius. This one was 25 degrees Celsius. None of those are 0. They weren't standard temperature. And 1 atmosphere is standard pressure, and this one was only a half of an atmosphere. And this one was over an atmosphere. So Pertner works under non-STP conditions. So the first part of the homework is doing gas problems when the gas is at STP. Again, at STP, 1 mole of a gas takes up, should have written this with more space, 22.4 liters of space. So number 1, find the volume of 0.3 grams of carbon dioxide gas at STP. Well, if I have 0.300 grams of CO2, let me really quickly convert this into moles, because grams is almost always useless. Carbon, oxygen, oxygen, how much does CO2 weigh? Got 12 plus 16 plus 16, 44. If I remember right, I think it's actually 44.01. That's how much a mole of CO2 weighs. Grams, grams per mole. That'll tell me how many moles I have. And I just learned this new chunklet. I'll do it in a new color. New conversion. 1 mole of gas at STP. At STP. Takes up 22.4 liters of space. So 1 mole of gas at STP, which it is, takes up 22.4 liters of space. Grams cancels, moles cancels. I'll be left with liters, which is what I want because it says to find the volume. Equals 0.3 divided by 44.01 times 22.4 equals 0.153 liters. That's the volume that this gas will take up at standard temperature and pressure. And this conversion, 1 mole of gas at STP is 22.4 liters. This applies to literally any gas at STP. It doesn't matter if it's CO2, doesn't matter if it's CO, doesn't matter if it's N2. It literally includes every single gas. If it is at STP, then it will be 22.4 liters of space. So right now what I want you to do is, we obviously are not done with the notes because we only made it halfway down the paper, but hold off on these notes for a second, and I would like you to work on 15A, the homework 15A, finish number 2, 5, 6, 7, 8, 9, 10, 11. And actually, you can go all the way to the section on the back where it says Dalton's law of partial pressures. Everything else, I want you to try. Take like 15 minutes. If you have a hard time, like just get as far as you can, skip it, and then watch the video where I go through how to do some of them. My biggest recommendation is to go through first and do the conversions, like 500 milliliters. Milliliters needs to be converted to liters, stuff like that. And then when it asks you questions like, what is the density of something? Oof, we haven't talked about that yet. But you know that density is mass over volume. So if you go through a Pervner calculation and you find volume, you should be able to figure out the density, right? So just do your best, get as far as you can, and then there'll be a tutorial video to help with some of the problems once you've struggled your way through these problems.